Welcome to today's problem walkthrough. In this session, we'll explore an intriguing graph problem titled All Paths from Source to Target. We'll break down the problem, understand its requirements, and discuss efficient approaches to solve it. Let's get started. In this problem, we are tasked with finding all possible paths from the source node, labeled as 0, to the target node, labeled as n1, in a directed acyclic graph, or DAG. The graph is represented as a list of edges, where each entry graph, I, contains a list of nodes that can be directly reached from node I. For example, if graph I contains j, k, it means there are directed edges from node I to nodes j and k. The goal is to return all these paths as a list of lists, where each inner list represents one valid path from the source to the target node. The output order does not matter, as long as all valid paths are included. Let's take a look at some examples to better understand this setup. Here is the first example. The input graph is represented as 1, 2, 3, 3. This means that node 0 has outgoing edges to nodes 1 and 2, node 1 has an edge to node 3, node 2 also has an edge to node 3, and node 3 has no outgoing edges. From this, we can find two paths that lead from the source node 0 to the target node 3. The first path is 0-1-3. And the second path is 0-2-3. These paths are represented in the output as 0, 1, 3, 0, 2, 3. This example demonstrates how we traverse the graph to find all valid paths from the source to the target node. Now, let's examine another example with a more complex graph. The input graph here is 4, 3, 1, 3, 2, 4, 3, 4. In this graph, node 0 has edges to nodes 4, 3, and 1. Node 1 connects to nodes 3, 2, and 4. Node 2 connects to node 3 connects to node 4, and node 4 has no outgoing edges. From this setup, there are 5 valid paths from node 0 to node 4, which are 0-4, 0-3-4, 0-1-3-4, 0-1-2-3-4, and 0-1-4. These paths explore all possible ways to traverse from the source to the target in this directed acyclic graph. Now, let's review some constraints and edge cases for this problem. First, the number of nodes n in the graph is equal to the length of the input list, and it satisfies 2 = n = 15. Each node I can only have edges to other nodes in the range 0 to n1, and there are no self-loops, meaning graph I cannot contain I. Additionally, all elements in graph I are distinct, ensuring no duplicate edges from any node. Importantly, the graph is guaranteed to be a directed acyclic graph, or DAG, meaning there are no cycles. For edge cases, consider the smallest input, where graph equals 1. Here, there is only one path, 0, 1. In a highly connected graph, such as graph equals 1, 2, 3, 4, 4, 4, there are multiple paths to explore. Finally, in cases where some nodes are disconnected, such as graph equals 1, 3, paths may not exist for certain nodes. In disconnected graphs, it is possible for no valid path to exist between the source and target nodes. For example, if the graph is graph equals 1, 3, there is no way to traverse from node 0 to node 3. This is because node 3 is not reachable from node 0 due to the lack of any directed edges forming a valid path. These constraints and edge cases help us understand the boundaries of the problem and ensure that our solution accounts for all possible scenarios. To solve this problem, we first consider the brute force approach using a recursive depth-first search, or DFS. The intuition behind this method is straightforward, since we need to find all paths from the source node, which is node 0, to the target node, node n1, we can explore every possible path in the directed acyclic graph, or DAG, using DFS. Starting at node 0, we recursively visit its neighbors, keeping track of the path in progress. Once we reach the target node, we save the entire path to our result list. After saving the path, we backtrack to explore other possible options. While this method is simple and intuitive, it has significant trade-offs. The time complexity is 2 to the power of n asterisk n, as there can be up to 2 to the power of n paths in the graph, and storing each path requires n operations. The space complexity is also high, with n, for the recursion stack and additional memory for storing all paths. This approach, while conceptually straightforward, can become inefficient for larger graphs where the number of paths grows exponentially. Now, we refine the brute force approach into an optimized version of DFS with backtracking. Although a DAG naturally prevents revisiting nodes, backtracking ensures cleaner management of the current path state during recursive calls. The process starts similarly, where we use DFS to explore paths, but we explicitly manage the current path by removing the last node after each recursive call. This ensures that the path remains accurate as we explore other branches. When we reach the target node, we save the path as before and continue the search. The time complexity remains O(2 to the power of n asterisk n), as the number of paths is determined by the graph structure, and the space complexity also remains O(n) for the recursion stack and O(2 to the power of n asterisk n) for storing paths. While the runtime is no faster than brute force, this method is more structured and avoids redundant state management, making the code easier to implement and debug. It's a cleaner and more efficient strategy for handling the problem. Another approach we can use is breadth-first search, or BFS. Unlike DFS, which explores one path deeply before moving to the next, BFS traverses the graph level by level, exploring all possible paths simultaneously. This can be implemented using a queue to track the nodes and their associated paths. We start by initializing the queue with the source node, which is node 0, along with its path. For each node dequeued, we enqueue its neighbors, updating the path to reflect the nodes visited so far. When we encounter the target node, we save the path and continue processing the queue until all paths have been explored. The time complexity is O(2 to the power of n asterisk n, similar to DFS, as BFS also considers all possible paths in the graph. However, BFS tends to require more memory upfront, as it tracks all active paths concurrently in the queue. While both methods are equally viable in terms of time complexity, this higher memory usage is a trade-off to keep in mind when using BFS for this problem. For this problem, we chose the recursive DFS with backtracking approach. The key insight here is that the directed acyclic graph guarantees no cycles, making DFS a natural choice for exploring paths. Incorporating backtracking simplifies the management of the current path state, ensuring that each recursive call operates cleanly and independently. While BFS is a valid alternative, it involves managing a queue to store all active paths, which can lead to higher memory consumption in practice. The DFS with backtracking method strikes a balance between clarity and efficiency. Although the time complexity is exponential, O(2 to the power of n asterisk n), due to the nature of the problem, this approach avoids the overhead associated with BFS while systematically exploring all paths. This simplicity and efficiency make it the preferred strategy for solving the problem effectively. To solve the problem of finding all paths from the source node, node 0, to the target node, node n1, in a directed acyclic graph, DAG, we can use a recursive approach based on depth-first search, or DFS. The graph is represented as an adjacency list, where each node points to its neighbors. For example, in a graph like 1, 2, 3, 3, node 0 points to nodes 1 and 2, and node 1 points to node 3. The adjacency list representation helps us efficiently traverse the graph. The algorithm begins with input parsing, followed by defining a recursive DFS function. This function takes the current node and the path leading to it as parameters. The base case of the recursion checks if the target node is reached. If it is, the current path is added to the results list. This sets the foundation for systematically exploring all potential paths in the graph. In the recursive case of the DFS function, we iterate through all neighbors of the current node. For each neighbor, the function is called recursively with the updated path, ensuring that all edges leading out from the current node are explored. The initialization step starts the DFS from the source node, node 0, with an initial path containing just this node. A results list, called all_paths, is initialized to store all valid paths from the source to the target. Once the DFS completes, we return this results list. DFS is particularly suited for this task because it explores one path fully before backtracking, providing a systematic way to traverse all paths in the graph. Using recursion further simplifies the implementation, as the call stack naturally maintains the state of the current exploration. This eliminates the need for manually managing a stack, making the code cleaner and more intuitive. The algorithm handles both base and recursive cases seamlessly. The base case ensures that as soon as the target node is reached, the current path is saved as a valid solution. The recursive case ensures that all outgoing edges from the current node are explored, guaranteeing a complete traversal of the DAG. To achieve this, we use three key data structures. First, the adjacency list represents the graph efficiently, making it ideal for sparse graphs and enabling constant time access to neighbors. Second, a list is used to track the current path during exploration. By passing this list by value, we avoid unwanted modifications during recursion. Lastly, a results list, all underscore paths, stores all valid paths as lists of nodes, making it easy to retrieve and return the final output. Together, these structures provide a foundation for a robust and efficient implementation. Analyzing the algorithm's complexity, the time complexity in the worst case is exponential, 2 to the power of n, because the total number of paths can grow exponentially with the number of nodes in a complete DAG. Each node could potentially connect to all other nodes, leading to an enormous number of paths. For space complexity, the recursion stack can go up to O(n), where n is the maximum path length, as each recursive call adds to the stack. Additionally, the results list requires space proportional to O(p*n), where p is the total number of paths, and n is the number of nodes in the longest path. The code implementation reflects these principles, using a simple recursive DFS to explore all paths and backtrack as necessary. The algorithm is both compact and effective, leveraging recursion for clarity. To see the algorithm in action, consider the graph 1, 2, 3, 3. The output of the function for this graph is 0, 1, 3, 0, 2, 3, representing all paths from the source node 0 to the target node 3. This example demonstrates the algorithm's ability to correctly compute all paths in a moderately connected graph. The algorithm also handles edge cases effectively. For instance, in a single-node graph the output is 0, as the source is the same as the target. In a graph with no connections to the target, such as 1, the output is an empty list, as no valid paths exist. For highly connected graphs, the algorithm ensures that all paths are computed accurately, even when there are multiple routes to the target. These examples highlight the versatility and correctness of the approach. When handling large graphs, it's critical to ensure the algorithm operates within memory constraints. The adjacency list representation is space efficient, especially for sparse graphs, and the recursion depth is limited by the path length, which is typically smaller than the total number of nodes in the graph. However, the exponential growth of paths in highly connected graphs means that the results list could become a bottleneck. Efficient memory management and early termination in cases where paths are not needed can help optimize performance. Overall, the algorithm is well suited for exploring paths in directed acyclic graphs, balancing simplicity in implementation with the ability to handle edge cases and varying graph structures. This Python implementation solves LeetCode problem 797, all paths from source to target, using a depth-first search (DFS) approach to explore all paths in a directed acyclic graph (DAG). We begin by defining a class solution with a method allPathSourceTarget. The method takes a single input, graph, which is a list of lists representing the adjacency list of the DAG. Each node has a list of its neighbors that can be directly accessed. A helper function DFS is defined within the method to perform recursive DFS. The DFS function takes two arguments, node, the current node being processed, and path, a list representing the current path from the source to the current node. Each recursive call explores one possible route starting from the current node. The base case for the recursion is when the node is the target node, which is the last node in the graph, len, graph, 1. When this condition is met, the current path is added to the result list. The path syntax ensures a copy of the path is stored to avoid mutation issues. For each node, we iterate through its neighbors. A neighbor is appended to the path, and the DFS function is called recursively for the neighbor. After the recursive call completes, we backtrack by removing the last node from the path, using path.pop. This ensures that the path remains correct for exploring other neighbors. The result list is initialized to store all valid paths from the source to the target. The initial DFS call starts from node 0 with an initial path, 0. After all recursive calls complete, the result list contains all paths from the source to the target node, which is returned as the output. This approach ensures that every valid path is explored exactly once. The algorithm leverages the properties of a DAG to avoid cycles and guarantees termination. With its simplicity and clarity, this implementation is both robust and efficient for the constraints of the problem. This is the Java implementation of LeetCode problem number 797, all paths from source to target. The logic mirrors the provided Python solution but uses Java's type declarations, collections, and structure. It employs a depth-first search (DFS) approach, starting from the source node 0 and exploring all paths to the target node N1. The result is constructed using a list of lists to store valid paths. Key differences include the use of Java's ArrayList for dynamic lists and explicit type management. The DFS method handles recursion, adding and backtracking nodes as needed to explore all possible paths. In this problem, we are tasked with finding all possible paths from the source node, which is node 0, to the target node, which is the last node in a directed acyclic graph or DAG. The graph is provided as an adjacency list, or each entry graph, I, lists all the nodes that have a directed edge from node I. To illustrate, let's consider the graph 1, 2, 3, 3. Here, the target node is 3, as it is the last node. We start a depth-first search, or DFS, from the source node 0, initializing our path as 0. From node 0, we observe that it has two neighbors, 1 and 2. First, we visit neighbor 1, adding it to our path, which now becomes 0, 1. Then, we continue our DFS from node 1, where the current path is 0, 1. At node 1, we see that it has one neighbor, node 3. We proceed by visiting neighbor 3, adding it to the current path, resulting in 0, 1, 3. Since node 3 is the target node, we add this path to our results and then backtrack. Backtracking involves removing node 3 from the path, bringing us back to 0, 1. Next, we backtrack further, removing node 1 from the path, returning to 0. From here, we explore the remaining neighbor of node 0, which is node 2. We add 2 to our path, making it 0, 2, and initiate DFS from node 2. At node 2, the current path is 0, 2, and we find that its only neighbor is node 3. We then visit node 3, adding it to the path to form 0, 2, 3. Since we have reached the target node again, we add this path to our results. Afterward, we backtrack by removing node 3 from the path, returning to 0, 2, and then backtrack further to 0. At this point, all neighbors of node 0 have been explored. For this graph, the final output consists of all paths from the source node to the target node. These paths are 0, 1, 3, 0, 2, 3. Now, let's consider a second example with a more complex graph, 4, 3, 1, 3, 2, 4, 3, 4, In this example, the target node is 4, as it is the last node. We begin the DFS from node 0, initializing the path as 0. Node 0 has 3 neighbors, 4, 3, and 1. First, we visit neighbor 4, adding it to our path, which becomes 0, 4. Since 4 is the target node, we add this path to the result and backtrack to 0. Next, we visit neighbor 3, adding it to the path to form 0, 3. From node 3, we observe that it has one neighbor, node 4. We visit this neighbor, reaching the target node, and add the path 0, 3, 4 to the results. Afterward, we backtrack by removing 4 from the path, returning to 0, 3, and then backtrack further to 0. Next, we move to neighbor 1, adding it to the path to form 0, 1. Node 1 has 3 neighbors, 3, 2, and 4. By exploring these neighbors recursively, we find 3 additional paths 0, 1, 3, 4, 0, 1, 2, 3, 4, and 0, 1, 4. When all possibilities have been explored, the final output for this graph is 0, 4, 0, 3, 4, 0, 1, 3, 4, 0, 1, 2, 3, 4, 0, 1, 4. Now let's look at a simpler example with the graph 1, 2, 3. Here, the target node is 3, and we start the DFS from node 0 with the initial path 0. Node 0 has only one neighbor, node 1. We add 1 to the path, making it 0, 1, and proceed to perform DFS from node 1. At node 1, the current path is 0, 1, and we see that it has one neighbor, node 2. We visit node 2, adding it to the path to create 0, 1, 2, and then start DFS from node 2. At this point, the current path is 0, 1, 2. From node 2, we find that its only neighbor is node 3. We visit this neighbor, adding it to the path, which becomes 0, 1, 2, 3. Since node 3 is the target, we add this path to the results. Afterward, we backtrack by removing node 3 from the path, returning to 0, 1, 2, then backtrack further to 0, 1, and finally to 0. As there are no other nodes to explore, the final output for this graph is 0, 1, 2, 3. To analyze the time complexity of this problem, we start by noting that we are tasked with finding all paths from the source node to the target node in a directed acyclic graph, or DAG. The algorithm uses depth-first search with backtracking to explore these paths. Let's break this down. If n is the number of nodes in the graph and e is the number of edges, the graph is represented using an adjacency list. In the worst-case scenario, every possible path in the graph is explored. Since we are dealing with a DAG, the number of paths can grow exponentially based on the graph's structure. For instance, if each node has up to k outgoing edges, the total number of paths from the source to the target can reach up to k(n1). For each of these paths, constructing a path involves a traversal that takes linear time, proportional to the length of the path, or O(n). This means that the total time complexity of the algorithm is given by O k(n1) *n***, where the exponential term arises from the number of paths and the linear term accounts for the traversal and construction costs. Here, k represents the maximum out degree of a node, and it plays a critical role in determining the complexity. This accounts for the exhaustive exploration of all paths and the time required to copy each path into the result list. In terms of the best or average case, if the graph is sparse and has fewer paths, the number of paths explored will naturally be smaller. However, the exponential term still dominates in the asymptotic analysis, meaning the worst-case complexity remains exponential. Now, looking at space complexity, there are two main factors to consider. First, the recursive call stack. The depth of recursion is determined by the longest path in the graph, which can be at most n. This gives a maximum space usage of O(n) for the stack. Second, we must account for the storage of all valid paths in the result list. In the worst case, the number of paths is k(n1), and each path can take up to O(n) space, leading to a total storage requirement of k(n1)*(n***). When we combine these components, the total space complexity is dominated by the storage of paths, which is k(n1)*(n***). Comparing this approach to a naive brute force method helps us appreciate the efficiency of DFS. A brute force algorithm would generate all possible sequences of nodes and then check each sequence to see if it forms a valid path from the source to the target. This would result in significantly worse performance, with a time complexity of O(n) in the worst case. On the other hand, the DFS-based solution avoids unnecessary computations by focusing only on valid paths, making it much more tailored to the structure of a DAG. However, the exponential growth in the number of paths inherent to the problem still remains a limiting factor. The DFS approach, while optimized, cannot escape this exponential blowup entirely due to the nature of the graph. The reason for this exponential growth lies in the branching factor k at each node. Each recursive call in the DFS explores all possible neighbors, leading to a total of k(n1) paths in the worst case. Additionally, constructing each path incurs a linear cost of O(n), as the algorithm copies the path list during backtracking. To summarize, the time complexity of the algorithm is k(n1)*(n***), and the space complexity is also k(n1)*(n***), with the dominant factor being the storage of paths. While the algorithm performs efficiently for smaller graphs, it becomes computationally intractable as the graph size increases, especially if n is large or the maximum outdegree k is high. This highlights the trade-off between problem complexity and algorithm efficiency when dealing with exponential growth in graph traversal problems. Here, we explore some common mistakes to watch out for when tackling this problem. First, failing to account for cycles in the graph can lead to significant issues, such as infinite recursion in DFS or algorithms failing to terminate. This is especially critical in variations where the graph isn't guaranteed to be a directed acyclic graph, or DAG. To address this, you can use a visited set to track nodes in the current path, or verify that the problem explicitly guarantees a DAG upfront. Next, inefficient handling of paths is another frequent pitfall. Reconstructing paths repeatedly, like appending to lists during every recursive call, can add unnecessary overhead. Instead, you can pass a single mutable list representing the current path and leverage backtracking to remove the last node after each recursive call. Lastly, ignoring edge cases, such as disconnected graphs, can also lead to missed paths or runtime errors. For example, if a target node is unreachable, your solution might fail. To handle this, ensure you explicitly check connectivity and account for isolated nodes in your implementation. Now, let's continue with additional mistakes to avoid. Using BFS instead of DFS without proper justification is a common error. While BFS is useful for finding shortest paths or specific metrics, it's not optimal for exhaustive path enumeration as it consumes more memory and doesn't leverage backtracking. DFS is generally the better choice here. Always select the algorithm that aligns with the problem's requirements. Another frequent issue is having incorrect termination conditions. Forgetting to stop recursion when the target node is reached can cause invalid paths or even infinite loops. To prevent this, ensure your base case is well defined so that valid paths are appended to the result at the correct point in the algorithm. Paying attention to these details will make your solution both robust and efficient. In interviews, this problem often serves as a test of core graph traversal and backtracking techniques. Recognizing the patterns is key. DFS is the go-to for exhaustive searches, while backtracking helps optimize path exploration. Interviewers may also explore optimization opportunities with you, such as reducing redundant path computations or minimizing memory usage. Be prepared for follow-up questions that introduce variations, like weighted graphs for shortest path problems or undirected graphs that might require additional handling. When these variations are presented, it's important to articulate how the changes affect your approach. Clear communication is critical. Explain your choice of algorithm, whether it's DFS or BFS, and how it fits the requirements of the problem. You should also be familiar with related problems, like LeetCode 207 for cycle detection or LeetCode 210 for topological sorts, as these can deepen your understanding of graph-based challenges. Finally, let's look at some alternative approaches you might encounter. Iterative DFS, for example, avoids recursion depth limits by using an explicit stack for state management. While this eliminates the risk of stack overflow, it does require careful handling of the stack manually. Another approach is BFS with path tracking, which can be useful for shortest path problems but can become memory intensive when enumerating all paths. Dynamic programming with memoization is another option. It optimizes repeated subproblem computations by storing intermediate results, but this comes at the cost of additional memory usage. Lastly, topological sort combined with path enumeration is a specialized approach for DAGs where pre-processing is allowed. This method can simplify the enumeration process but is only applicable when the graph meets specific criteria. Each of these approaches has trade-offs, so selecting the right one depends on the problem constraints and objectives. Great work following along. We've covered the problem all paths from source to target, discussed the recursive DFS approach, and highlighted key takeaways. Remember to practice regularly, as graph problems are common in technical interviews. Thanks for watching, and don't forget to like and subscribe for more tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!